All right. Today we're going to finish up the unit on power markets, and actually that finishes the entire unit on power systems in general. So of the three big units of the course, remember, we first had machine learning, then we talked about some power systems, then we're going to talk about control last. And so today we're going to start that third unit on control. And control in some sense kind of brings together all these things, right? Because machine learning, we motivated it as when you want to understand a system, maybe can't write down analytical properties of how the system behaves, then you want to use things like machine learning to estimate the properties of that systems from data. The power systems as well, when you can estimate certain things from physical principles, you probably want to go ahead and do that. And so that was what that unit was largely about. We learned how to kind of model grid scale phenomenon of energy, of electricity at least, in that context. And now finally, control in some sense kind of puts this all together, because the ultimate goal of these systems should really be to make decisions in some sense that, say, improve efficiency or reduce the cost of energy, etc., maybe reduce emissions. So control in some sense is going to be bringing this all together, the idea of predictions and the idea of physical laws, in order to now actually make decisions about how we should act. And that can be decisions about, maybe long-term things like what sort of generators should we build over time, or very short-term things in terms of, how should this battery pull in or push out energy according to the current grid conditions. So it really spans a wide range of things. We'll mainly focus on kind of the more shorter-term things, though, in terms of, a time horizon looking forward of days or weeks maybe, but probably not many, many years, at least in our context here. And today I'll just, this will pretty much take up the rest of the class as unit on control. So it will also bring together things like how do we actually enforce the constraints of the power grid? How do we actually use predictions from machine learning to enable us to perform these control actions? But today we'll start off with a pretty straightforward example of how you might do control and basically some basic definitions of what optimal control is in this context. And we'll talk some about heating, building heating, and then energy storage, like in a battery. So before that, though, we're going to finish up our unit on power markets and finish talking about power markets. Remember, these are how we currently provide electricity to consumers. But actually, before that, I want to mention, though, we do have the homeworks, right? So the homeworks, the third homework is out today. It's posted online now. It is due 2 weeks from today, so we will have the Friday office hours before that. That's the week before Thanksgiving. It'll be due on the Tuesday. We'll have office hours the Friday before, and then the next homework will be due out either that day or probably actually on Thursday that week. The other thing is that the solutions then to the last problem set are now posted. They can't use any more late days at this point. Or I guess if you're taking it now, you've already used up all your late days. So the solutions are now posted. And you can download them from the website. It's the same login as before. If you don't remember that, just let me know. I'll tell it to you. But I'm just not writing it down here because I want to keep this as much as I can off the off the free internet at least. So are there any, well, the other thing is I guess I'll be handing back the homework on Thursday, the corrected homeworks for problem set 2. Were there any questions about what we talked about last time or the homeworks or really anything? Okay. If there are, just let me know. All right, so finishing up power markets. Oops, I didn't get my little clicker. All right. Now remember, I motivated power markets by saying that this is a little bit different than most markets for a lot of goods, right? Selling electricity is a bit different in that we can't wait for bids and market prices to kind of reach some equilibrium point. In the meantime, you turn on a light switch and it doesn't actually do anything, right? We really want to treat, in some sense, demand as being inflexible. So there is just some demand. And we have to coordinate a market with different competitors to immediately satisfy whatever demand that might be. It's also different because we can't store energy. And a lot of kind of the market equilibrium ideas implicitly, in some sense at least, assume you can store goods, so that if you can't sell a good right now, you could sell it 5 minutes from now, and that wouldn't cause any big problems. But with electricity, you want it right now. And it maybe doesn't matter if you can get electricity 5 minutes from now if you don't have it right now. I guess this was what I said before, the demand is viewed as fixed, not as some flexible good, which will actually vary depending on the price. You know, we might have some differences in consumption based on the price of electricity, but that's a pretty minor factor in a lot of consumption, these days at least. Prices just aren't that high to really make people want to do that just for the sake of money. Maybe a little bit in kind of long-term things like maybe heating and cooling. You might think about the price. But for a light switch, if I want a light right now, I don't think about what the price of electricity is right now before turning on that light switch. And then finally, the distribution of this product here, electricity, has to obey these physical laws that have constraints, right? Most goods you can just put in a truck and you can ship somewhere else. I guess that's some cost involved to that, certainly. But with electricity, you really can't just take some amount of electricity generated somewhere and consume it somewhere else without consideration of the power flow that this actually causes. So all those physical laws we learned about in power flow are relevant to how you actually create this market. And so all these together create some very interesting situations in power markets. And the way it works, I mean, in some sense it's sort of hard to imagine this could possibly work, right? How could power markets work in an open market at all, given that the open market kind of is about competition, right? So you want to have people competing to generate maybe lower cost power, but how do you really have that while assuring that at all times you will in fact meet demand? It's kind of tricky. When there was one monopoly that owned everything, it was a little bit easier, right? Because then they could just decide, well, look, we have to generate this much power. We're going to balance kind of our internal costs maybe as in some optimal sense, but that at least was easy for the utility for a single entity to do. And when you have a lot of different generators independently producing power, it's not even clear why this will really work in some sense. And in fact, what they do in practice, you can't really have kind of a traditional open market for these reasons exactly. You can't just have generators operating on their own with no concept of sort of what's really happening, and making deals one-on-one with consumers as the day goes by. That just wouldn't really work here. So what happens instead is that everything is run through this independent system operator called the ISO. There's also called regional transmission operators, which is a little bit different due to some legality issues, but they're basically the same thing. It's essentially a system operator that plays the role of the utility in the old monopolies of power. And so they are not a utility themselves. They do not actually generate the power, or at least typically don't. But they coordinate all the generators and all the loads together in a market mechanism. And the reason why you need this is you need some central source, right, to actually say, okay, we have all these loads that we're going to treat as just fixed, and we have to meet them. We have a bunch of generators that have different costs, different sort of competitive structure. How do we actually coordinate that all that in an instantaneous manner? You really need some sort of centralized source to do this. And the way this works is that this ISO here acts as kind of the intermediary between the loads and the actual generators. So the loads you can think of as being reported to the ISO. They don't quite report it. The ISO actually does some forecasting what these loads are, and also meets instantaneous demand through through some other mechanisms there. But you can think of it as the ISO gets some reporting or some estimate of what these loads are going to be, right? Then, in addition, the generators all submit bids to the ISO that are kind of in the form of like a cost function, right? So remember, when we talked about optimal power flow, there were costs you could associate with different generators. And so the generators actually report those costs to the ISO. And these may or may not be their true costs. They can also try to game the system if they want to. that's actually perfectly fine. If they think they can make more than what it actually costs them, they have to make a little bit more, in fact, or it wouldn't be a very good business. But they report some notion of their cost to the ISO, and that is essentially, how does your cost to generate power increase with the amount of power you produce? That's what they report to the ISO. The ISO uses these two things, the loads and the costs, and they solve this big optimal power flow problem, the kind that I showed in the last setting, right? We have generator costs, we have loads that have to be met, we also have constraints on the grid. All these things have to be taken into account. The ISO solves a big power flow problem, optimal power flow problem, and that determines what generator is going to generate what. All right, so in the end, the solution to this is these generators generate this much power, these generators generate this much power. So it solves that problem, gets those power generations, and then sends those back to all the generators and say, okay, here's how much you have to generate. And there are legal contracts that are binding in some respects where if you bid into the market here, you have to be able to generate that. So you cannot falter on your bid, or if you do, there's actually at least a big penalty. So you maybe buy it from some other secondary source, but you pay a big penalty in the meantime. They all generate their power now, and then power flows just as it will, right? Obeying physical laws, these power flow laws, to actually provide power to the consumers. But because they took into account these power flow laws when they scheduled everything, they actually will ensure that no constraints are violated in terms of overloading lines or maybe generating too much power at a plant, things like that. Those constraints will all be satisfied. And this happens about every 5 minutes. So this is a quite detailed and kind of involved process they do very often to allow for the fact that we do want to have some sort of competitive market, yet we also need to coordinate it centrally. Now, in terms of what that particular power flow problem they solve is, it's just an optimal power flow problem, but it's kind of specific. I mean, the cost or the objective function, for example, is almost always the cost of energy. And so it is a special case of optimal power flow that they're all solving to actually route energy or to schedule generation and route electricity in this sense. So just to sort of describe that particular problem, I'm going to talk about the optimal power flow solution that you solve for a power market. So optimal power flow is a broad term, meaning any optimization problem that you can solve that involves some power flow constraint, really, whereas power markets are a particular instantiation of that. And to make things a little bit clearer, I'm actually going to, at each node, instead of having each node be either a generator or a load, I'll actually say that each node can have both of these things, right? So each bus has a generator and a load. If there is no generator, in fact, you can just constrain that generator's power output to be 0. That would just be the constraint you put on to account for the fact that there is no generator there actually. And if there's no load, similarly, you just have the load to be equal to 0. But really, this is just sort of for convenience sake more than anything else. And then we'll just say that the actual power injection at each node is equal to the generated power minus the power of the load. And this will be handy because there are some nodes that have both generators and loads. And actually, more importantly than that, though, for computing things like prices at each node, you really want to be able to talk about what's the price for generating more energy in terms of if that node consumed more energy. So you want to have the ability to have loads at each node. Okay, so a typical optimal power flow for these power markets just takes the following form. The idea is you want to minimize the cost of generation here. Right, so remember, the superscript G will refer to generator power, The superscript L will refer to load power. And PS here is going to have a real and reactive component, which is going to be P and Q respectively. And in general, though there is some cost in some sense to generating reactive power, we typically only put a cost on real power, because that's really what you have to actually generate at the generator itself, right? If you want to produce power, you have to use some amount of fuel, for example. That fuel will produce a force on the turbine, and that will create the real power. So this is really what we think of as having a cost is the real power. So we want to minimize the cost of all generators in typical power markets. That's the objective. And that's just the sum from I equals 1 to n, that is over all the generators, the cost for that ith generation. And if you can't generate anything, then you would actually add a constraint that a certain node couldn't generate anything, and so it wouldn't matter what the cost was, because that would have to be equal to 0. Okay, so we want to minimize this cost of all generation, which is really the total that everyone is paying, right, altogether, subject to a few constraints. The first one of these is just the power flow constraint, right? Oh, I'm saying minimize over Z here. Remember, Z is our concatenation of the voltage angles, voltage magnitudes, power, all that kind of stuff. That's the same as in the optimal power flow specification. So this first one is just exactly the same as before. It is just the it's just the power flow equality constraint, which is just saying that, remember, S here, the actual total power injection is equal to the generated power minus the load power. So this is just saying the power injection here equals this term, and that's just the power flow equations that we had before. So obviously, right, anything you schedule has to obey power flow, so you better obey that equation there. This next one's a little bit different. And what it says is that this is an expression for the power that flows from node I to node J. Complex power that flows, in some sense, from this node to that node. Because this would be the current that flows from I to J here. And then times the voltage at the source node, that would be the power flowing from one to the other. It's actually not the same as the power flowing the other way, or the negative power from the other way, because there is loss in the line. So depending how much loss there is, this could actually be different than the reverse there with Vj, but it's essentially, it's approximately the same, considering those are usually not that far apart. And you typically just constrain the bigger one of these two anyway. So basically, every line, for example, may have a maximum power it can transmit. And so you want to ensure that the power you send over any given line, really the current that's flowing through any given line, is not bigger than some maximum amount. You could do it in terms of either current or power, but both actually have their uses. And then finally, there may be some other ones as well that you'd want to write to, like all the normal power flow constraints, like the voltages have to be fixed maybe at some nodes, the loads will have to be fixed at other nodes, but I'm just kind of writing some of these terms here. The other one is that the generator power has to be less than some maximum power each generator can produce, right? So each generator cannot produce infinite amounts of power. They have to be constrained in some sense. This is just an example. There are other things you probably want to add here, as I mentioned, like maybe you have some constraints on voltage angles, for example. You can't have voltage angles too far apart, or some instabilities become concerns, so you constrain them in that sense. You'll probably also add constraints on reactive power, things like this. Generators can't necessarily produce a lot of reactive power, or a huge amount of reactive power, maybe. Or maybe it's constraints on what would be other good constraints? I guess you'd also just have the equality constraints, right, of saying the loads are known here. And in fact, actually, SL here is just assumed to be known in some sense for these problems. So again, this is not a complete description, but it hopefully gives you some idea of what the optimal power flow problem that you solve for power markets is. The important part is the objective is the cost of generation. The constraints are, first of all, the power flow constraints, and second of all, things like line constraints or generator constraints. And you'll see a lot of different examples of this when you read a paper on power flow. They'll all have kind of their own notation for this, but this is basically the idea of what they're doing in those constraints for optimal power flow, typically.
SG minus SL, do you want that to be close to 0?
No, not necessarily, because I mean a lot of you don't have generation in any given node, right? So you don't have a generator every node. So some nodes just have loads. That would be implied by if this constraint here being 0. And I guess you also have to make the power also greater than 0 always. You don't want to have generate negative power, I guess. Yeah, no. So you definitely need to have. Sometimes it has to be out of balance because some places you will just have negative L here. You will not have any generation. And in that case, you need to supply that power from somewhere, so it has to flow from the network. If you had a generator and a load at every single node, which could supply all the power that node needed, then of course, well, not actually, maybe, and if they all have the same cost, for example, then of course you would just generate them all at those nodes because you would only incur losses if you transmit it over the grid. But we don't have that, right? Some nodes just have loads, no generation. Some have just generation, no load. And so you need to think of this the same as power flow. There are going to be power injections at different nodes. That's what SG minus SL is. It's just that you want to separate out conceptually what those two things are. So this is getting to be a fairly complex statement here, right? We're getting pretty detailed in terms of the actual number of constraints we add, kind of the physical ramifications of each one of these constraints. Getting pretty detailed, but hopefully the big picture is still fairly intuitive here, right? We want to minimize cost, subject to power flow, and then some constraints on generation and some constraints on the lines. That's all we're writing here. Are there any questions about this? Okay, so the last thing I want to mention is this whole process, in some sense, can be viewed as kind of a black box, where the input are the loads. That's what we actually assume are known here. So loads are known, and we're actually just optimizing the generation at each node. And so I guess this is kind of odd notation here in some sense, but we just take a set of loads to start with, plug them into an optimal power flow solver, and what we get out are, Z star, which is both the generation at every node as well as things like the voltage angles, the real and reactive power for each node, and we of course also get a cost for that solution. Right? That solution incurs some cost to generate that stuff, so we get both the optimal solution, how much power we should generate, and the cost for that. And the last thing I want to mention now is this notion related to power markets of locational marginal prices. So remember, in this theory of the firm we talked about a while ago, the marginal price was the cost for the incremental cost for making kind of one more item, right? It was the derivative of the cost function with respect to what you're producing. In power markets, there is an analogous quantity, but the interesting thing is because power actually has to obey these physical laws and has losses between nodes, you actually get a case where the price of power varies at different locations in your network. So this is very different from most markets, right? Because in most markets, there's one marginal price for a good. Okay, it will just be whatever the derivative of the cost function is with respect to the number of things at the point of what you're producing, the derivative with respect to the number of items. And that's just one marginal price for everything. In power markets, you have this interesting case where because of the physical properties of the system, because I can't just generate power here and have you have it instantaneously over there without any losses and without any transmission, you get this phenomenon of locational pricing, where you actually have different prices at different parts in your network. These can actually be very, very sizable, these differences, when you have constraints on transmission, for example, or when you have constraints on how much different generators can actually produce. And formally, the locational marginal price, or it's also called nodal pricing sometimes because they price the different nodes, it's just going to be the cost per unit of a little bit more power consumed at node I. And formally what that is just, remember, our optimal power flow solver gave us Z star as a function of the loads everywhere. And so the LMP is just the derivative of that global cost with respect to consuming a little bit more at node I. So what it's really saying is, if I were to consume one more unit of electricity at node I, how much would that increase the total cost? Where unit is a very small, sort of incrementally more amount. And in fact, some people are working on this for their projects. If you look at an ISO like PJM or an RTO like PJM, RTO stands for Regional Transmission Operator. It's the same thing as an ISO. It's just a little bit different from a legal perspective. They actually will publish lists of the LMPs in their network at every single generator, every single substation, and also aggregated over their different areas here. And this is important because this gives some idea of how much the price of electricity kind of really, what is the real price of electricity? Not only, not the price you get in your bill every month, because they kind of fix that by amortizing over what they expect it to cost in reality, but what is the real cost that they are actually paying to get energy at a given location? Yeah?
So LFP is not an attribute of generator, but an attribute of the load?
It's an attribute of a node in a network. So there are LMPs at both load nodes and generation nodes. And what it is an LMP is what it would cost if you wanted to consume a little bit more at that node. So if you were a generator and you have not yet reached your maximum production, then it's actually pretty simple to compute the LMP. It's just going to be the derivative of your cost function at that node, because you can just generate a little bit more, and provide it to your node if you wanted to consume a little bit more there. Even if there's no actual consumption going on at a generation node, you still consider it in terms of what it would cost to generate more power for the current node. But at a generation node, if you're already at your maximum amount of power, then the LMP will actually not be that derivative, right? Because you will, in order to get, if you're generating sort of the maximum power at a generator, and you want a little bit more power there, you would need to actually get power from somewhere else. Similarly, for a load node, those also have LMPs, right? Loads in the network also have LMPs. And what that is just, if I was going to consume a little bit more at that node, what would the price be then? And that would have to take into account things like, well, I can't generate it here. Wherever I generate it, I have to get it from somewhere. So what's it going to cost, both in terms of what they are adding and in terms of if there are constraints in place right now, how do I actually account for those constraints, right? That makes all these kind of weird situations arise where very odd things can happen. We won't go into the odd things that can happen, but very strange things can happen, indeed, because of these features like this. The fact that you have constraints on transmission and you have losses in the network.
For example, I have an LMP in my
No, they're typically for distribution nodes, so substations essentially. I mean, I guess you could have an LMP at your house, but really they don't think about marginal prices at your house. Think about it at a substation level, and then you ultimately just pay a fixed price for your energy. So you just get it from your substation, and then sort of the actual network from the substation to you is quite a bit different than the transmission network. So actually, that's another thing we should mention. All this is really about, for the most part, transmission networks. Maybe secondary transmission networks, but still to the substation level. Not to the level of from the substation to your home, which is called the distribution network. This is much more about the transmission network here. And so to actually compute these things, well, we could just compute it numerically, right? We could add a little bit. We have an optimization problem. We could just go ahead and add a little bit to our loads, see how this is the cost, and then compute the derivative numerically to compute these things. It also turns out that a lot of the times you can actually compute all these things automatically using what are called dual variables in the optimization problem. We're not going to go through how that works actually, but it's just sort of, you should know that the compute LMPs, they are in fact not just going through every, not running this optimal power flow problem n times for the number of different buses they have. You actually can just solve it once, and you get a lot of these things kind of for free when you solve the actual optimization problem. Just as an aside, it is done. That's how it's done in practice. It's not done exhaustively with numerical derivatives. The 830 version of the homework will actually have a problem of computing LMPs, and there you can just use numerical methods, right? You can just add a little bit to your load, see that changes the cost, and then divide by the change in cost by the change in load to compute the numerical derivative.
P is load or the power.
P superscript L is the real power of the load. And they're typically formulated in terms of real powers. You could potentially do similar things for reactive powers here. The problem with reactive power is that losses of, quote unquote, losses of reactive power, which is a little bit strange to say, but basically the amount of reactive power that kind of dissipates over a transmission line, because reactances are typically much higher than resistances of transmission lines, right? They have actually a relatively high inductance versus their resistance, these transmission lines. Because of that, the actual losses you get in reactive power are very big compared to losses in real power. And so reactive power does not really operate in the same sense. You can't really hope to provide reactive power to a location very far away. They'll just lose so much transmission that it makes it very uneconomical. What you do instead is you actually use local kind of generation, and it's generation not the right word. Something like a capacitor, for example, could produce reactive power. And you can do it with other things like voltage control and kind of other mechanisms you can use to supply reactive power. But that has to be done kind of locally. And so because of that, because power markets are really about kind of large-scale transmission and the cost for this, the LMPs are done always really in terms of what happened there. In terms of reactive power, of real power. I think I decided it was a good time to update my software maybe or something like that. Okay, well the last slide is just text, so while it's doing its thing, oh, maybe it's not. Okay, so the last thing that I'll mention, okay, yeah, it's, okay, maybe. The last thing I'll mention, oh, so I'll give an example first. So here's just an example of this 3-node network we had before, 3-bus network. Each node, each generator has a cost associated with it. These were the same ones we saw last time, where one was cheaper at first, but then gets more expensive. And the other one is more expensive at first, but then gets cheaper with different quadratic penalties, essentially. We'll also put a load on both these two things here. So there are also some consumption going on here. And there'll be a third node with no generator, but just a load. Now, I'm not going to go through the details here, but essentially, if you compute the optimal power flow here, you solve it, what you get is you get that the LMPs at the different nodes are equal to this thing. And it's kind of intuitive here because, and again, I won't look at the actual numbers here, but basically, the bus without a generator, as you might expect, has the highest cost of energy because in order to get electricity here, you have to generate it at one of these two places, but then there's also losses in the lines, right? So you're paying both for the power you actually get as well as the power that is lost in transmitting it to you. And this happens only sort of more so when you have things like constraints, because then you pay both for the power that you get as well as kind of the dance you have to do with other generators to ensure that no constraints are violated. Yeah?
So for the other two nodes, it just supplies the power directly. It has no power flow?
No, there is power flow between these two. What you'll notice there is, so this one here, this one might be generating it all actually. So if there is a load at this node, you will, and I guess in this case it probably would actually in fact be generating it all here. If there is a load and generator at the same node and neither one, and the generator does not hit its maximum amount, then you will always just use that power to provide your current load too. And you'll do that, I mean, it's not obvious why you do that, but you do that for physical reasons because essentially on a bus, there is considered to be no loss there. And so it's always kind of best, if you can, to provide your power to your own load there. If you are at your maximum capacity though, and you can't generate anymore, then you still need to get power from other loads as well. Here in the case of they are not either of them at their maximum generation though. So this load had 1 and this load had 0.1, and so in fact the generators are big, the generation is bigger than that. I guess they were megawatts, the units here. And so they will in fact be providing their entire load. There probably will, there will though be some power flowing here though. Because of power flow, some of the generation here that goes to this one will probably take this path. So there will be power flowing along this line here. It's just that they also are both providing their own load. And in some sense, sort of the power you provide versus the power that just comes into your node and maybe leaves, it's all ambiguous, right? Because if power is supplied across this line in one direction, then there is just sort of, in some sense, more power here. So what you produce versus what you're just consuming there is kind of ambiguous, right? I mean, all electricity is the same in some sense. There's no difference between electrons that come from over there in some sense. That's not really how it works. And so in this case, it was sort of intuitive, right? Because the LMP, as we expected, was highest at the node without a generator because it needed to pump in power from elsewhere. The interesting thing is that this can actually cause some very complex issues, which we won't go into it all here. I just want to highlight the fact that these things do exist. So if you look at the prices on, for example, PJM, and you can actually go to their website and look at the LMPs for every single node in the network, you'll find that some of these are actually negative. Right? So some prices can actually go negative sometimes. And this is very strange because the power, the sort of the cost of generation for a generator is never negative. They never sort of can generate energy and make money just by using up stuff. So what's going on? And what's happening is that when you have constraints in the power grid, there can be times where in order to get more power to a given node, you have to reschedule generation in a lot of other different places, kind of in very non-intuitive ways, in order to ensure that you're not going to overload that one line and still generate more power there. And at some locations, this will actually cause the power, if it's an increase in power at one location, would actually cause the total cost of power to go down when you consume more power. right? Because you could have some generators that are sort of, maybe you can't use generators that you were going to use that were kind of really high cost because they would overload the lines. You have to use other ones farther away, maybe that are cheaper to generate at those actual, I mean, in terms of the actual cost there. And so that, you know, and pick a different flow through the network from that, or result in a different flow through the network. And that can actually cause, at certain nodes, the price to be negative. Now, you always kind of pay for that by having higher prices elsewhere in the network. You're not ultimately making money out of the system. You are paying for that elsewhere. But at a given node, you can actually have a situation where you are asked to consume energy. So if you had a battery, that would be a really good time to charge it, because they would pay you to charge your battery right then. Again, not as a consumer typically, because as a consumer, you can often not buy directly into this for some good reasons too. I mean, you probably don't want to, I think actually later on in the slides, in the next set of slides, I have some graphs of LMPs, and they can really be very variable. They can really spike to be in the hundreds, almost $1,000 per megawatt, which is really expensive for power, right? But you don't want to be exposed to that, presumably as a consumer. You'd rather just have your utility kind of take care of everything and you pay a flat rate. Though there are more and more people that are moving to structured rate plans to account for some of that, but even there, it's typically not that you pay the actual LMP at, you know, the closest node in the network. It's more that you just have a, you know, some sort of tiered pricing that changes at different set times and things like that. But essentially, all these things are issues here. The fact that you have transmission constraints and power flow equations causes lots of oddities when you talk about locational marginal prices. We're not going to go into that, but just be aware that these things do exist, and there's a whole big field that has evolved out of power markets and out of how do you understand power markets. And in fact, there are even more elements to power markets than just LMPs and just optimal power flow. So in reality, you don't just run one power market currently at the sort of the current time. You actually use it to do both day-ahead scheduling. So you'll run it both one market a day in advance to kind of get your basic allocation of different generators set up. Then using your current forecast a day ahead. Then 5 minutes ahead, or maybe an hour ahead, or 15 minutes ahead, you will, which is called the real-time market, you will, given your new estimate of what the demand is going to be, and given your old scheduling that you've already laid out, you determine essentially, well, how should I actually add a few more generators or turn a few of them off? Or how should I schedule generation to account for the fact that, you know, my prediction was not particularly accurate, was not guaranteed to be accurate a day ago. What should I do right now? The market handles a certain portion of providing energy. If you are, again, I sort of use the example of we want to turn on a light switch and know that it's going to come on, right? But the power market, I mean, even though we solve it pretty frequently every 5 minutes or so, that's still not fast enough to account for someone turning on a light switch, right? So on top of this, there are a number of what are called regulation services or ancillary services that essentially provide fast-acting support to the grid that it sort of accounts for that. Actually, this is not quite the same thing as reserve, so let me just also mention this. But there is the need to kind of track in very, very exact amounts, make sure that sort of the current generation exactly equals current consumption, even though that can fluctuate randomly from second to second. And so there's another set of services that are not viewed in a market way. They basically are just paid for. You pay a generator to have that kind of ready to go, and you have the ability to kind of bump up and down very, very quickly to account for current changing demand. And then also reserve, which is a little bit different, but can be a similar thing here, is essentially a margin you have over what you expect to need, right? So say we make a prediction that we're going to be consuming, 2.8 gigawatts of electricity in PJMs and Duquesne lighting, not in PJM, but in Duquesne lighting zone tomorrow. We probably actually want to schedule a little bit more than that, because we probably want to have a little bit of a margin there where if we do err, and we probably will, it's better to err on the side of caution, right? So you actually have a little bit more than what you thought you had. And so this term reserve generally means power that is available, that can be turned on, but is not actually being provided to the grid right now. Someone mentioned before reactive power, right? What about reactive power? And as I said before, you can't really treat it in the same way as real power here because the losses are so high. You typically don't think of it in terms of markets. You think of it much more in terms of services to the grid, like regulation services or like reserve. And finally, a really big issue is transmission. The problem with transmission is that if you start up a generator, remember we have limits on transmission. If you start up a generator, you will just have your power flow according to the power flow equations, right? You can't say, oh, I only want my power to flow over this transmission line and not this other guy's power. Power will just flow as it does. And so the question is now, well, who actually pays for transmission then? If I buy transmission, how am I going to know that I get my value for it when other people can use it as well? If I'm a utility and want to buy more transmission, what should I do there? And how do I account for the fact that there may be overloads in the transmission system, so I may not be able to provide power even though I kind of, I bid it, I sent my bid into the market. Maybe just to the real-time market, there is just no way I can produce that amount of power because of these transmission constraints. And this is sort of after the actual power flow, maybe a new sort of event happens where you can't transmit power anymore. So all these things cause really big issues and have been dealt with extensively in the literature. Again, we're not going to go into detail here. Sort of power markets even are kind of one small portion of this course. The bigger portion even on the electrical grid was more about the physical side of things. But power markets are a huge, huge domain. There's a lot of depth you can go into here. So if people are actually curious about these things, I'd be happy to chat more and recommend some additional sources you can look at to find out more about these things. But this ends our unit now on electrical power systems. And from here, we're going to go on to control systems and talk about control. And it's a really nice segue in some sense because a big constraint of control systems, when we talk about grid level control, are things like power flow constraints and things like the fact that these systems have to obey physical laws. So if you want to decide how to schedule generation, not just this instant, but actually over time, how do you go about doing that? And these now become a class of problems we're going to call control. Before we move on to that, though, are there any questions about electrical power systems in general, I suppose? Yeah?
So how are those LMPs connected to the price we pay?
So what utilities do is they essentially look at what they expect their actual prices to be, and then they will charge you some sort of amortized amount. They will basically charge you, if they're going to charge you a flat rate, right? They charge you more than what electricity usually really costs. So they charge you more than the average LMP, or maybe more than the most common LMP. But they actually account for the fact that there are those big jumps. So even if they are paying for a little while and you're getting power cheaper than they can actually provide it, they still win in the end because they charge you a rate that's usually higher than the current price of electricity. Actually, maybe I can really quickly pull this up. Let's see if I have. Actually, I won't do that right now. Because I have a graph of it in the next section, so maybe I'll just go with that. If you're curious, I can show you in the video. You can go if you go to PJM's website, you can also take a look at their actual LMPs, and you can kind of see the price. And the price is usually pretty low compared to what we pay for electricity, on the order of I think like 3 cents a kilowatt or something, 3 cents a kilowatt hour or something like that. But of course, there are some spikes where it goes to a whole lot more than that. So you have to be able to account for those things. Okay, so let's talk about control.
One more.
Yeah.
So it's responsibility to do those reactive compensation.
It's viewed as a service, so you get paid for it, just like you get paid for having reserve. It's not the I mean, not like my responsibility. I don't provide my own reactive power. No. It is a service that the ISO will buy from, say, utilities, right? So utilities can also have local reactive power supply, as an example, and they will be paid for that, not in the same way as they are paid for power. They don't get paid kind of from what they generate. They just get paid for the service of providing reactive power support. We pay it ultimately in our price, right? That's another way was when the price is higher than what it actually costs them in terms of LMPs. We pay them some flat rate, and then the ISO determines how much reactive power support is worth how much.
So I mean, for example, so if I didn't use any reactive power, like I don't have some synchronous machine, or I just use light, so why should I pay for those?
Well, also in the same way, why should you pay for anything more than the current LMP of your price, right? They don't know what you're using, and so you have to, and even if you don't use reactive power, I mean, there are reactive losses in transmitting to you. So you are using reactive power just in the sense that power has to get to you, even if your power factor is 1. So all these things, you have to, in fact, that's probably the bigger loss, because reactance is very high along long transmission lines. So you, as a customer, don't want to have to pay for that, sort of, see the exact amount you own. You just want to pay a flat rate. And a lot of actually energy bills are I know that this actually corresponds exactly to that, but energy bills oftentimes correspond to things like transmission is one item that just charges you a fixed amount, and then the actual power you buy is another item. And so you pay for it kind of from your bill, but you don't pay for it directly. You pay for it, and then they buy it. The ISO or someone determines how much you need of this, or someone else sometimes also, but determines how much you need of all this, and then you ultimately will be paying them for that.
If you're paying the bill to utilities,
Yeah.
how does ISO?
Yeah, so utilities are the ones you pay for, and some of their money will go to the ISO, and some taxes go to the, I believe, I'm actually not quite sure on that, so don't quite quote me on this. They probably are, I mean, they are public organizations. So they are not for-profit institutes, or companies rather. They are public organizations. And so, I don't know if there are any that might be for-profit. I don't think so. But anyway, they're very heavily regulated, at least. So they have lots of regulations governing what an ISO can do. And so where they get their money from, all this kind of stuff, is governed by the actual laws of the regulations setting these things up, which were enacted when they got rid of those monopolies and enacted the sort of the market structure for generators. Okay, so the little bit of time we have left, I want to start introducing control as a topic. And we won't get very far today. We actually might not get to either of these examples here. But I want to give some basic definitions of what control is and why it's really an important thing to study when we talk about the smart grid. So far in the course, we've really been focused on problems that, things I'll call like allocation problems. Or just prediction problems that aren't really dependent. I mean, they might depend on time, but there isn't really a temporal nature to these things, right? So for optimal power flow, for example, we had some loads, and we want to say, right now, how should we schedule generators to meet these loads? Similarly, for machine learning problems, for prediction problems, we would say, okay, given some temperature, some maximum temperature, what is the most or so, how much demand do we expect people are going, or how much electricity do we expect people to actually consume given that high temperature? And that's really kind of just a prediction that isn't really dependent on time, right? It's dependent on something like just the input, which is just the maximum temperature. And even if you had say time of day as a feature, and you're trying to predict load at every time, machine learning by itself isn't really that temporal nature, at least not what we've done so far, because we're just treating it as kind of a fixed problem still, right? Where we just have a fixed set of features as input and then an output we're trying to predict, which isn't really temporal in nature. It's just a sort of a fixed mapping there from input to output. Control, broadly speaking, is going to be about tasks that now, where these temporal components are kind of very, very important and are going to have to be accounted for. That's not really a technical definition of control, but broadly speaking again, control is concerned with tasks that have this temporal nature. We have to make decisions over time or decide allocations that change over time. Those are kind of the things we talk about when we talk about control tasks. Systems also that evolve over time, that aren't just static, but actually evolve according to some laws that change over time. Or even that are static, but just depend, the next state depends on the past state, essentially. And we'll use this term, control tasks, to talk about settings where we want to minimize some or optimize some objective, say minimizing some kind of cost. And by here I don't mean actually just sort of monetary cost anymore. I mean kind of any cost. We want to minimize some notion of cost in some kind of dynamical system. And I'll find what I mean by that a lot more in a second. But there's a notion of systems that have some kind of state to them, and we want, and maybe that state evolves over time, and we want to minimize cost in one of these dynamical systems. And that's the basic idea of what a control task is, for the purposes of this course at least. Now, these are really kind of ubiquitous in energy and sustainability problems, right? Control tasks, well, in the real world, almost everything is temporal in nature, right? We are, in fact, beings acting in time. So it's not surprising that energy tasks often have a very important temporal component as well. So things like, for example, heating or cooling a building in response to changes in occupancy, for example, right? Well, the heat of a building is a state in a system, right? It isn't a thing you decide every single time. You can't have a heater that sets the temperature in a room instantaneously. All you can do is pump in more heat or let it cool down slowly. But there is this sort of mass and state to the system because temperature does not change instantaneously. Similarly, occupancy probably also has state too, right? Occupancy, it's not a random variable where I am jumping in and out of a room randomly every instant. There's probably some sense in which if I'm in a room, I'll probably stay there. And there's some sort of momentum here. Something like storing electrical power in response to some renewable generation and maybe also electricity prices is also a case where we have a state. Namely, we have the state of the battery, something that we might want to keep track of, right? Because you can't just say the battery, the whole point of the battery is you can actually charge it and discharge it. And it's probably the case that you cannot charge it to full capacity in an instant. You have to charge it some over time. So the state of charge of this battery becomes a state of a system. And you have to make decisions that actually take into account the fact that, okay, I want my battery to be at this level now, but I can't sort of take that all out instantaneously, so I have to kind of charge it slowly over time. Maybe discharge it slowly over time as well. Also, things like pricing even does have some notion of state. The price, though it is quite variable, does not fluctuate randomly, just like random noise. It has some sort of state where if it's in a certain level, it tends to stay in that level. Same with things like renewable resources. If the wind is blowing, it probably will keep blowing. Not for maybe a day ahead, but maybe for the next 5 minutes. There's some momentum to the system. And I'm using the term kind of things like momentum and state. And I'm doing that kind of intentionally because I want to drill in the fact that what's interesting here is that the system is not one where you can arbitrarily set the state to whatever you want. There is some sense when we are constrained by what we can do with the system by some sort of natural dynamics to the actual physical system, right? We can't cool the room or heat a room instantaneously. We can't charge a battery instantaneously. And so we have this notion of a state to the system that we have to sort of evolve over time. Something else like maximum power point tracking. If you want a system like a wind turbine or a solar panel to be generating the maximum power it can, you actually want to track different operating points. It depends on external conditions, but you also have constraints like you can't change them too fast and things like that. And finally, even something like generation scheduling, where you actually have to take into account the temporal component rather than just the instantaneous component, which is what we kind of thought about in terms of optimal power flow. So a very good example of this is a lot of generators, they cannot start up instantaneously. A lot of generators use boiling water to drive turbines, either steam generation. And steam generators, in order to start up, they need to actually boil water first, right? And a lot of water, they have to boil first. So if that's just cool water, you can't get that going immediately. You have to actually take some time to start these things up. And because of that, a generator, say, if you ask it to start now, it won't actually be ready to produce power, say, for 3 more hours or so, some generators. And so even in scheduling, and when you're doing it kind of in a sense where not just we want to schedule it right now, assuming we have the ability to turn on everything instantaneously, if you want to say, okay, I have a day ahead, and I want to schedule time for power for every interval in that day, how should I do that in a way that actually takes into account the constraints of the generators as well as these power flow constraints we have? So again, the sense of all these things are situations where you have some notion of what I'm calling state. And so let me actually define what I mean in a little more detail, put into definitions. And these are still a little bit they're a little bit informal still, but they're good to kind of have some sense in mind what I mean formally by state and control or input, and then finally what a controller is. And I think, unfortunately, we might have to actually end after this slide. No, I think we have a little more time, sorry. So we'll hopefully get into a few more ones afterwards. I was thinking we were 10 minutes ahead. So the state to a system. Again, introducing now the third set of notation for the class. And I apologize for using one set of notation for machine learning, one set for power systems, and then now another set for control. But the reality is these are I'm kind of using the common notation for each of these domains individually. And it's very good to be familiar with that, because you will see this when you read a paper on control or on machine learning. You will see this notation, so it's good to be familiar with all of it. Hopefully the one I'm using will be clear from the context that I'm using it in. So the first element I want to talk about is the state of a system. We're going to call it a vector x, which is going to be an n-dimensional vector. This was the exact same notation we used for input for machine learning, but now here it means state. And in fact, it does not mean input anymore. Input's another character. What the state captures, in some sense, is the elements of a system that determine how the system evolves, but which we cannot directly affect. So a great example is temperature in a room. The temperature in a room will affect what the next temperature is, right? Because temperature tends to, not change too rapidly. But we, as a controller, would not have the ability to directly affect temperature. In that we cannot just say, okay, the temperature here is 68 or so, and okay, now it's 80, right? We can't do that. What we can affect is what's called the control input. Oops. This is represented as a vector u in Rm. And these are the elements of a system that also affect its evolution, but which we can directly control. So a good example for the temperature case is this would be, for example, a switch on a heater. Or even just you can think of it as the energy we inject in the heater, or the power of the heater maybe. That's something we can set, because we can instantaneously, for all practical purposes, turn on a heater in the room. That will affect temperature, but we have complete control over this. We can make it whatever we want at every time. So if I want it on now, I can turn it on. If I want it off, I can turn it off. I cannot set the state however I want it to be in a system. And then finally, a controller, also called sometimes a policy in kind of the more machine learning bent on control, but typically it's called a controller in the control literature. This is going to be a mapping from states to actions. And in fact, this is not, it can also be a little bit more than this, but this is sort of the simplest case of a controller. It's essentially a controller prescribes what we do with control given the current state of the system. So a controller I'll call pi, which is a mapping from states to controls. So again, in our heating example, a control policy could be if the temperature is below 68 degrees, turn the heater on. And if it's above 70 degrees, turn the heater off. And otherwise, keep it what it was before. This is actually a little bit more complex of a controller because this actually depends on past states. Actually, let me revise that. Let's just have a controller that just says, sorry, that would depend on past control too. So let me have a controller that actually just says, if the temperature is less than 68, turn the heater on, otherwise turn it off. That would be a control law that prescribes control actions, whether the heater's on or off, given the state of the system. And a big part of optimal control is, well, given the state, but maybe also some past states too, maybe some past controls as well if you want to include those too, determine what control action we should take to maximize some objective. So the goal of a lot of control is to come up with a controller given some information about the system itself. Now, importantly though, what are these systems? We just defined the state and the control so far. We actually have to define the system. And one of the most important elements of control is this notion of dynamical systems. So this sort of formally defines exactly how states and controls impact the evolution of the states. In particular, the dynamical system just describes how this state evolves as a function of both this state and the control input. So we'll talk about this in a second. We'll actually give an example of what this is. But for heating, for example, it will just be, for example, the thermal equations about how heat dissipates given external input and given, say, leakiness of a room or something like that. That could be an equation for how state evolves given the current state and the control. And in general, this can be a very complex relationship here. Right? Because the future state could potentially depend on all the past states you've seen and all the past controls you've seen, according to this definition here. Right? So say we're having discrete time. So I'll talk about discrete and continuous time down here below. But we could have a case where the state at time t plus 1, say, is some big function in the state at time t, t minus 1, t minus 2, etc., and also u at t and t minus 1, etc. Right? That's possible. That's still a valid description of a dynamical system. But in practice, and in fact this is kind of almost, for a lot of people, to define what state is that we're going to think about what are called first order systems. Which is different than linear first order systems. So the order of a system in some sense for a linear system does not have to be the same as the order I'm talking about here. I just mean by first order, all I mean is that the state at the next time depends just on the state at the current time and the control at the current time. And it's first order because we do not consider any past states in defining our dynamics. So this is a very restricted subset, it might seem like, of dynamical systems, but really it's still very powerful. Because, for example, if we had a true state where the system really depended on the past n different states, we could actually still encode that as a first order system, right? Just by making a state include not just the state at time t, but also past states as well. And having those evolved is kind of, well, the state at time t minus t becomes state at time t minus 1, etc. So this is actually not that much of a simplification here. In fact, this is a general formulation of what a state dynamics can be. And so it's much easier to work with this than trying to explicitly work with systems that have dependence on a long sequence of past states as well. So we're going to work exclusively in this class with first order models here. The exception being things like autoregressive models, which I know plenty of you have actually looked at for your homework. These are you can think of them as dynamical models, and we'll cover this actually more in the next lecture, or the one after the set of slides, in terms of talking about things like autoregressive models, which are kind of dynamical system, but they're also means for predicting stuff like in machine learning. So we'll talk about this a little bit, but essentially, for the most part here, don't worry about that yet, we'll talk about that in the next set of slides. What I want to say here is that for the most part, we will talk about these first order systems. So we're going to talk about systems where the dynamics is of this form. And really there's two very common forms for first order dynamics. And the first one is this right here. So the first one is a discrete time formulation. That means we think about the system at a discrete set of points in time. And we talk about how the system changes from one discrete time slice to the next slice. And there's no sort of inherent notion built into this notation of how big that time really is. So is this 2 seconds ahead, or 1 second ahead, or a millisecond ahead? This notation does not make that clear here. All this is saying is that there is some notion of a discrete set of time points, and this equation governs how the system evolves from one time point to the next, where we only care about the system at that finite number of time points. And we actually will almost always use this one. Actually, before I say we're going to use that, let me describe what the other alternative is. The other potential system is what's called a continuous time system. And here, we actually describe the system in terms of a differential equation. So what we say here is that x dot, which is equal to the derivative of x over time, the instantaneous derivative over time, equals f of x and u at the current time. Now what this is saying is this is actually very similar to this. This is just giving you a definition of what the derivatives look like, what the instantaneous changes look like, given the current state and given the current control. And in fact, it's easy, kind of approximately, to convert between the two, because if you have a differential equation like this, you can always apply something like Euler integration. So actually, how many people here have heard of Euler integration before? Just by a show of hands. No one? Someone has to have heard of Euler integration. Yes? I see some nods, but no hands. So I feel a little more, okay, I'm going to assume everyone does. If you don't, come talk to me. Essentially, for any system, you can approximate a discrete set of evolutions of that system by taking xt plus 1 equal to xt plus a little bit of its derivative, right? So plus some delta t, where delta t now corresponds to the actual time increment between these two different slices, times the derivative of x. And here that would just be this function. xt ut. So clearly, the discrete time, at least in its approximate sense, this is now a discrete time equation. So we can just sort of fold this delta t into the function dynamics itself, and these two we can convert between each other. You can do the same thing for approximating a continuous time system using essentially finite differences of a continuous, or sorry, you can approximate a continuous time system by using finite differences of a discrete time system. That's a little bit less common though. Now in this class, we're going to use almost exclusively the discrete time formulation. And the reason really is that, except for some very specific cases, when you're going to solve these things on a computer, and there are no analytical forms of the continuous time state evolution, you're going to ultimately do some sort of numerical integration anyway. You're going to do something like Euler's method here. So, I mean, a computer can't store an infinite sequence of points in time, right? So we need some sort of discrete representation anyway. So we'll just go ahead and use the discrete time formulation. Oftentimes, if you want to look at these things more mathematically, it can be cleaner, certain systems at least, if you want to sort of really get in depth into them, it can be cleaner to look at actual differential equations and how those things evolve. But it's really a matter of oftentimes pretty small changes. The math is actually oftentimes very, very similar between these two different settings. And because we're using computers here, because we're going to be solving these things, we are going to use almost exclusively the discrete time formulation of dynamics. So let me just preface this, and I'll end after this. I just wanted to mention that there are a lot of extensions, both extensions and special cases, to this system, which we're going to cover in the next set of slides. But here I just want to sort of give a brief idea of what control is, even in these kind of simple systems. So, for example, we could have cases where the true state of a system is not known to us. Whatever the state is, it has things that we can't directly observe. All we can observe maybe is some function of the actual state. There are also cases where we might have some uncertainty in the dynamics. And this could and in general, this goes on under the heading of stochastic systems. We might have a case where it's not as if this evolves deterministically according to this equation, but there actually is some random noise in our system. And so we add some noise term, which I'll refer to as epsilon t, though again I'll define this a little bit more rigorously shortly, that actually says that, well, we don't really know what the next state's going to be. We just know it will have some distribution given the current state. Another very special case, which is really good to know, is a Markov decision process, which is a way of capturing stochastic systems in a very general sense, but it is typically not tractable except for the case of a relatively small number of discrete states and discrete actions. But a Markov decision process is just another way of modeling dynamical systems, particularly systems that are stochastic and that occupy discrete states with discrete actions is what they're particularly good for. But all these are special cases of, or actually not special cases, but generalizations or slightly different takes on the dynamical systems, which we'll cover. But we're going to wait until we've gone through a few examples of control tasks before getting to more detailed cases like this. Okay, so that's it for today. Tomorrow we'll pick up on, or Thursday we'll pick up on talking in more detail about some examples of control tasks and the kind of things you can do with control, and in particular, looking at control, as everything else in this class, as optimization problems, and why that's a very nice formulation to have for control. Great.